Hi there, it's Mr. Ray here with our next lesson in grade 12 advanced functions. We are working in the rational functions unit. We're on the fourth lesson. We've learned about what rational functions are. We've learned about how to determine vertical asymptotes, horizontal asymptotes, zeros, so x-intercepts, y-intercepts, and be able to do a sketch of what the graph looks like. In the last lesson we learned that when we're trying to figure out the horizontal asymptotes, we were looking at the degrees of the numerator and denominator. If the degrees were the same, such as linear over linear, the horizontal asymptote was the line y equals and then the ratio of the leading coefficients. If the degree of the numerator was less than the degree of the denominator, the horizontal asymptote was y equals 0. So that left a few cases. What happens when the degree of the numerator is bigger than the degree of the denominator, such as a quadratic over a linear, or cubic over quadratic. So we're going to be looking at one very specific case today, and that's when the degree of the numerator is exactly 1 higher than the degree of the numerator, such as quadratic over linear, cubic over quadratic, but it wouldn't be the case with a cubic over linear because that has a degree that's 2 higher. So that would be a totally different case, which is something we're not going to be doing in this course. So in the case where the degree is 1 higher on the numerator than the denominator, we have what's called an oblique asymptote. So we're going to do a couple of examples of those situations, how you graph it, what's different. Now an oblique asymptote, you cannot have an oblique asymptote and a horizontal asymptote. It's either one or the other. Okay, so in the case where the degree of the numerator is 1 more than the denominator, then you have an oblique asymptote, you don't have a horizontal asymptote. Okay, all the other rules apply for the vertical asymptotes. Vertical asymptotes have nothing to do with oblique asymptotes. Okay, so they don't cancel each other out or one or the other. You can definitely have both. Now, we're also going to be looking at one other certain situation, and that's something called a hole. And that's a hole in the graph, like a black hole. Now, this actually has something to do with the vertical asymptote. So we'll look at 2 examples of those first, and then 2 examples of oblique asymptotes. Okay, so here's the definitions. A hole is a point on the graph of the rational function where there's no defined value, so it's a hole. This occurs when you have a common factor in the numerator and denominator of the rational function. So I will do a little example down here in a second. Oblique asymptote, it's an asymptote that is not vertical or horizontal, but it is a line, and it has a linear equation for that. So it's a line. It's not vertical or horizontal, but it has some slope, okay, other than 0 or undefined. Oblique, or sometimes they're called slant asymptotes. I'll always call them oblique, but you might see slant when you're looking online. These occur when the degree of the numerator is exactly 1 more than the degree of the denominator. We've said that several times now. Okay, now let's look more at the situation with the hole. So I'll give you an example of a function that has a hole. So f of x equals x squared minus 1 over x plus 1. Now, one thing that we're gradually learning over time with rational functions, definitely the denominator. We always want to factor that if we can, but also the numerator. So obviously the denominator is just x plus 1. So I'm going to put brackets around just to emphasize that it's a factor as well as an expression. And if I factor x squared minus 1, that's a difference of squares. That's x plus 1 and x minus 1. Now you'll notice that I have an x plus 1 x on both the numerator and denominator, and yes, you can cancel them. And what you're left with at this point is just x minus 1. But there's a little bit more to it than that, because there's some hidden information here, because if I just gave the equation f of x equals x minus 1, you could say, well, I could plug in x equals 1 here, no problem. And that would be true, but if you tried to plug in x equals minus 1 here, you're going to have a problem, because the denominator would be 0. So in this situation where we have two factors that are the same in the numerator and denominator, and we can cancel them, well, that actually creates a hole, because if we go back to what we canceled, well, x cannot equal -1, which kind of gets hidden now because we've canceled that. So this fact that x can't be -1 means we're creating a hole there. So there is a hole at x equals -1. And because, so normally you might not look at that and say, oh, there's a vertical asymptote at x equals -1. No, because they canceled, there's no vertical asymptote. Okay, so if you do cancel factors, the factor on the bottom does not create a vertical asymptote. So in this case, it's a hole. So no vertical asymptote at x equals -1. Okay, so what would this look like on a graph? So we can actually start off by just graphing. Well, the first thing we look, is there any vertical asymptotes? Well, not anymore. So there's no vertical asymptotes. There's actually not even a horizontal asymptote in this situation, because it's no longer a rational function. It's just a linear function with an asterisk because of the hole. So we actually draw this line. So hopefully you remember how to draw lines. Slope is 1, y-intercept is -1. So I've got a point there, and I've got my slope of 1. So there's my line. Now that would be, x minus 1, but we do have a hole at x equals -1. So right here, I'm actually going to erase part of that line, because at that point there at -1, I'm going to have a hole. So I draw an open circle, which you should be familiar with because we've seen this before. That means there's no defined value there, but there is on every other point along this line. So that is a hole, and this is our f of x graph. Okay, so it doesn't even look like a rational function in this situation, but you can tell the fact that there's a hole along it probably means the original function was a rational function that we could simplify into linear in this case. Okay, so that's how that works. So just to repeat what I've already said, when the denominator can equal 0 and it does not cancel out, you get a vertical asymptote. So there could be situations still where you had another factor on the bottom that didn't get canceled out. In that case, you would still have a vertical asymptote. And you'll see that with our examples. If the 0 can cancel out, you get a hole in the graph. So canceling factors creates a hole. Now, an oblique asymptote, and we're going to look at two examples of these, occurs when the degree of the numerator is exactly 1 more than the degree of the denominator. So this is very important. This is one of the two key things we're learning. Obviously, how to find out if there's a hole and how to find out if there's an oblique asymptote. So basically, this is the important information that tells you there's an oblique asymptote. And the way we actually find out what the equation of this oblique asymptote, remember, it will be a line. It's going to be a slanted line, which is why sometimes it's called a slant asymptote instead of oblique. It won't be a horizontal line. It won't be a vertical line. It'll be some other line. Okay. Now the way we get this equation is we have to go back to our polynomial unit, and we're going to divide out. So For example, if your original equation was quadratic over linear, you take the quadratic and you divide by the linear expression. And then whatever whole part you get will be your equation. The remainder is not part of your equation. We'll see that in a second. And this basically just says you cannot have both horizontal asymptote and oblique. It's one or the other. Okay, and that totally depends on the degrees of the numerator and denominator. Okay, so let's move along. So we're going to do 4 examples, like I said, 2 regarding holes and 2 regarding oblique asymptotes. So the first one looks like it's going to be a hole. You can see, you might look at that and go, oh my God, this is degree 2, degree 1. I'm going to have an oblique asymptote here. But before we get there, let's factor everything. So the top I can factor into x plus 1, x minus 2, and the bottom is just x minus 2, and lo and behold, we have the same factor on the top and the bottom, which means that is going to create a hole. So when I simplify this, when I cancel, x plus 1 is our resulting linear equation for f of x. So I can say f of x equals x plus 1, and I have a hole at x equals, so if I set that factor to 0, I get x equals 2 is where the hole is going to be. Now notice for this one, because I've canceled out, it no longer even looks like a rational function. I don't have to do, I don't have to look at the vertical asymptotes and obviously the horizontal. There's no asymptotes remaining here, so I don't have to do all that calculation like we've been doing so far, and that's only because the resulting function is linear with a hole in it. Okay, so we go straight to our graph. Okay, now we look at the slope, we look at the y-intercept. It's got a y-intercept at 1, so that's here, and the slope is 1, so I'm going to be going up 1, right 1, down 1, left 1. So I'm going to have a line. I should use a ruler, but I'll trust my hand on this one. Okay. Now I have a hole at x equals 2, so I got to go back and fix my line, because at x equals 2, that point right there, it actually is undefined. So I go to where x equals 2, and where the line intersects that point, I draw a little open circle, which is my hole. So this is f of x equals x squared minus x minus 2 over x minus 2. Okay? So very important you draw the hole, otherwise it would just be this, just be linear to begin with. Okay, and this is my line that I drew, which is y equals x plus 1. Okay, so there's our first hole. Let's go on to our next example. So this time it says hole or asymptote. So sketch the function g of x, identify any holes or asymptotes. So anytime you get a question on a test or homework, most of the time they're not going to tell you what you're going to find. You have to go through a process of determining for yourself, what are my vertical asymptotes, what are my asymptotes, do I have a hole, and what's the behavior for those things. So again, first thing we always want to do is factor the top and bottom of my rational function. So in this case, I only have a linear on the top, so that's also a factor. So if I factor the bottom, I get 4x minus 3 and x minus 1. And yes, I do have matching factors, top and bottom. I can cancel those. So effectively, my function becomes 1 over 4x minus 3. Now this time, this did not turn into a linear function, so I will have a graph that has attributes of a rational function. So I'm going to have to do that necessary work. So the first thing I can definitely say is there is a hole because I canceled those factors. So I have a hole at, if I can't set that to 0, x minus 1 equals 0, so x is 1. So there's my hole. Now I still have a factor on the bottom, so that could cause the denominator to be 0, 4x minus 3 equals 0, and that would occur when, so I have a vertical asymptote at x equals 3/4. If I set that equal to 0, I get x is 3/4. I could also put 0.75 because it's exact. A horizontal asymptote, okay, when I look at the degree of the top is 0, the degree of the bottom is 1, so the degree of the top is less than the degree on the bottom. That means my horizontal asymptote will be y equals 0. No calculation needed. Okay, x-intercepts, y-intercepts, let's do those now. So x-intercept, I'm setting y equals 0, which means I want the top to be 0 here, which it can never be. So there are none. And that kind of makes sense because the horizontal asymptote is the x-axis. So I wouldn't expect usually to have a point along there. And the y-intercept, if I set x to 0, I get 1 over -3 or -1/3. I'm not going to change that to a decimal because it doesn't convert exactly. So I'll leave it as -1/3 for my information list. Now I'm going to do the vertical asymptote behavior. Okay, and I know vertical asymptote at 0.75, so I'll be approaching that from both sides. So as x approaches from the left, or as x approaches 0.75 from the negative side, I know that y will go towards infinity. Which one we don't know. Do that in a second. And then we do the other side from the right, the positive side. And now we just determine the sign of these infinities. Okay, so now we go back to our equation here. So if I'm approaching from the left, that would be like 0.74. So if I plug in 0.74 here, I'm going to get something less than 3. Something like 2.9 something. So 2.9 minus 3 will result in a negative. I have a positive here, so positive or negative is negative. So that means I have a negative infinity that I'm veering off to. And now if I plug in, say, 0.76 to reflect coming from the right side, 0.76 times 4 is greater than 3. So the bottom will be positive, the top is positive. So I'll be approaching positive infinity. And then the end behavior, hopefully by now you're doing this much quicker than lesson 1 or 2. And we know that x approaches negative infinity. We know that y will be approaching the horizontal asymptote of 0. We just don't know from the top or bottom. And so I'll do the rough statement here without the sign. And now if I plug in, say, for negative infinity, if I plugged in -100 here, I'm definitely going to get a negative number on the bottom, positive up here. So I'm going to approach 0 from the negative side. And if I plug in, a value that, for positive infinity, let's use, again, I'm always using positive 100. That's going to be 397 on the bottom, positive on the top, so that's going to be positive overall. And I've got all the information now that I need, so I'm going to do my sketch. Okay, now when I'm making my scale here, I've already kind of pre-thought, you know, what values am I going to need to plot here? Looking at my asymptotes and any x and y intercepts, I want to make sure that they're going to fit. Nothing worse than doing half a graph and realizing you have to do it again. Okay, so again, the first things I'm going to plot here are my, well, I'm not going to do the whole until later, but the vertical and horizontal asymptotes. So I've got 0.75. So that's my vertical asymptote. My horizontal asymptote is the x-axis, y equals 0. So I'll just put a dashed line slightly above. Okay, so I've got my asymptotes. Intercept, x-intercept none, but y-intercept is negative 1/3. Okay, vertical asymptote behavior. As I'm approaching from the left, I'm going down. As I'm coming from the right, I'm going up. So I got my two arrows for that. And then the end behavior. As I'm going towards the extreme left, I'm coming from below 0. And as I'm going towards the right, I'm coming from above, positive side. Okay, so I plotted all the information. Now I'm always going to start in the zone that I have the most information, and that would be this zone down here. I've got two arrows, and I've got my one and only point. So I'm going to just turn this sideways so I can do a better job. So this has to come out here and then take a sharp turn to go down to negative infinity. Now for this area here, I want to make this as symmetrical as I can. Now that because that point was quite helpful, so I'm not going to do something like this. I'm going to come way down and then branch off at the, and hopefully those look fairly symmetrical. Otherwise, not such a good job at the sketch. Okay, now the only thing we're missing here is the hole. So I have to go. Now I could have plotted this before, but I personally prefer to do it after. So I erase there and I go up to where my original sketch was, and I put an open circle at that point just to show there's a gap at that. There's a hole right there. Okay, so there's my sketch. You can see I've got vertical asymptote, horizontal asymptote, I've got a hole. So this one is the first of this type. So you can definitely have a hole, and you know, have all the other attributes as well. Okay, so that's our final example of a hole. Let's keep going. So this example here, obviously from the title, you know there's going to be an oblique asymptote. Okay, now I'm going to make a little note here. So the first thing I'm doing, well, I guess the first thing I should do is factor. Okay, so when I factor the top, I get x plus 3, x minus 2. So obviously your factoring skills are still important, and then x minus 3 on the bottom. Now, you notice this time we don't have any canceling involved, okay, because nothing in common, so there's no hole. Okay, so we can definitely say, I'll just put no holes here. Now it is possible to have more than one hole, but obviously the degree of your numerator denominator would have to be at least quadratic. Okay, so no holes here. Now the thing I want to point out is looking at the expanded version or standard form, we have degree 2 over degree 1. That's a difference of 1. So the numerator has a degree that's 1 higher than the denominator. That means I'm going to have an oblique asymptote. So I'll just put a little statement here for this one to state how we know this. So degree of numerator, which is 2, quadratic, is exactly one more than the degree of the denominator which is 1 because it's linear. So therefore h of x has an oblique asymptote. Okay, now you don't have to write this every time. I'm just doing this so that you can see how I knew there was an oblique asymptote, because I looked at the degree, one higher on the top. Okay, so we'll get to that in a second. First thing I want to do is are there any vertical asymptotes, and that factor is still on the bottom. It wasn't canceled, so I do have a vertical asymptote at x equals 3. Now the oblique asymptote, you have to be, I know it's going to be an equation, so it's always going to be y equals, because it's going to be linear. How do I get this? Well, let's do this over here. So now you need to show this work, but it's kind of like a side work, like as if you were factoring or something, that you would need to show some work to see where this came from, okay? So this goes back to our long division of polynomials. So I've got x squared plus x minus 6 divided by x minus 3. Okay, so I got to multiply this x by x to get that x squared. So I put an x there. X times both of these, so that's x squared minus 3x. Oops. X squared minus 3x, and then I'm going to subtract. So x minus negative 3x is x plus 3x, so it's 4x. Bring down the minus 6. And now I'm going to multiply by 4, positive 4. So I get 4x minus 12. And then negative 6 minus negative 12 is positive 6. Okay, and this is our remainder. Okay, so in terms of the equation of the oblique asymptote, we don't include the remainder, but we will state the remainder because that's going to be useful later. Okay, but as far as the equation of the oblique, it's just the whole part that's up here. So this is x plus 4. So that's you can see this is a line. It's definitely not vertical. It's definitely not horizontal. It has a slope of 1, and that's going to be the oblique asymptote. So now I'm going to state the remainder here. Now remember, the remainder is this over the divisor, so 6 over x minus 3. And this will be useful in a sec. Okay, now we continue on. So we got vertical asymptote, oblique asymptote. Since there's an oblique, there's definitely no horizontal. And then we'll look at x-intercepts. So x-intercepts, that's where the denominator is, the numerator is going to be 0. So if I set both of these factors to 0, I get 2 x-intercepts, one at negative 3 and one at positive 2. And the y-intercept is when I plug x equals 0 here, so I get 3 times negative 2, which is negative 6, over negative 3, which is 2. Okay, now we do the behavior. Vertical asymptote behavior, do this exactly the same way as always. So this time we're looking at x equals 3. So as x approaches 3 from the negative side, y approaches some form of infinity. As x approaches 3 from the positive side, y also approaches some form of infinity. So this is where we plug our values in. So if I'm approaching from the negative side of 3, that's like 2.99. So that's definitely, factor is going to be positive. That's going to be positive. That's going to be negative. So positive, positive, negative results in negative. So this will be approaching negative infinity. Negative sign there. If I plug in a value to approximate approaching 3 from the right side, I would use 3.01. If I plug in 3.01 for each of these, I get positive, positive, positive. So that results in heading towards positive infinity. Now here's the new part. So listen carefully. I used to do this a different way, and I will mention at the end how an alternate method of doing it, but I've learned to appreciate this method as being a lot faster. So as x approaches negative infinity, we want to know what y is approaching. I'm just going to leave that for a sec, and the same thing for x going to positive infinity, y is approaching something. Okay, now this is going to be different because I don't have a value here because it's not a horizontal asymptote. The value that it's approaching is not a constant value. It's changing because it's heading towards a sloped line. Okay, so rather than saying a value here, I'm just going to refer to the oblique asymptote. So we know it's going towards the oblique asymptote, but again, is it coming from above or from below the oblique asymptote? Okay, so this is brand new. So I'll either put a plus or a minus sign for each of these. So how do we get this? Okay, so I'm not going to show the work all the time for this type of thing, but I think it's important for the first time. Okay, so let's do the negative infinity, okay? So what we're going to be calculating is what is the value of the remainder for a point that we're using, okay? It's a little bit hard to explain without the graph, but what I'm looking for is the value of y going to be the same as the oblique? Well, it's not going to be the same because it's approaching, but will it be higher or lower than the line? Okay, and the way I can get that is from the value of the remainder, because the remainder is what I add on to the line. It's the value that I add to the oblique asymptote y value to get where my curve is. Okay, so all I do is I plug in a value for the remainder. So if I'm looking at, let's do this one first. So oblique asymptote. If we're going towards like negative infinity, so we're going to approximate using, say, negative 100. If I plug in negative 100 here, so I'm going to put that here so you know what I'm doing. So if I say x equals negative 100 for this, x equals positive 100 for this, then when I plug it into the remainder will equal 6 over negative 100 minus 3, which is 6 over negative 103. And all I care about here is the sign. So the remainder is negative. So that means that y is approaching the oblique asymptote from the negative side, from below. Okay? And I do the same thing here. This time I'm plugging in x equals positive 100. So in this case, the remainder is equal to 6 over 100 minus 3, so that's 6 over 97, which is definitely positive. So the remainder is positive. That means this is coming in from above the oblique asymptote. So y is approaching oblique asymptote from above. So I can go back now and just put those values in. You'll see how we use that when we do our sketch. Okay. So let's do our sketch here. Okay, so we've got to be a little bit careful with the scale. So I'm going to make it a little tighter than I did before. I think I'm going to go up by 2s. So 2, 4, 6, 8, 10, 15. -2, -4, -6. -2, -4. Okay, so let's start. Okay, so again, the first things we always draw are the asymptotes. Okay, so I do have an, if I go back up here, I have a vertical asymptote at x equals 3. I'm going to try to draw a little straighter now. So x equals 3. Okay, so approximately there. Now the oblique asymptote, I don't have a horizontal as a reminder. So the oblique asymptote has a y-intercept at 4, and it goes up by 1. So this would go up here. Okay, so I did a couple of sample points just to be able to draw my line. And now I'm going to do using a ruler or some straight edge. Okay, so now I have my oblique asymptote. I'll just put OA here and VA here as a reminder. Now in terms of points, I have 2 x-intercepts. I have one at -3 and one at 2. And I also have a y-intercept at 2. So that's a whole bunch of points compared to most of our questions. Now in terms of the behavior, so I'm going to draw my arrows. So as I'm approaching 3 from the negative side, I'm coming here. I'm going down. So I put an arrow here. And as I'm approaching from the right side, I'm going towards positive infinity. So I put an arrow here. Now here's where this is brand new, right? Because now instead of doing a horizontal asymptote, we've got this. So this should be pretty useful because as I'm heading this way on my graph, y is approaching the oblique asymptote from the bottom. So I'm coming up, approaching it from underneath. So I'm going to put an arrow right here. As I'm approaching from the towards positive infinity, as I'm going this way, I'm approaching the oblique asymptote from above. So again, this is brand new. And now we put everything together. We put all our information on the sketch. So again, this is, I'm going to have a branch of my graph down here in this pie-shaped piece. And I'm going to have one up here. I can tell, well, this one's pretty easy. I've got 3 points and 2 arrows. This one I've got 2 arrows. So I'm always going to do the one with the most information, which is obviously this one. I have to make this nice and smooth, but going through all the points. So that's not too bad. And now I'm going to do one up here. I'm going to use the shape of this as much as I can to determine the shape because it's basically symmetrical. So these are never perfect, but gives you some idea. Okay, so there is my graph, my sketch. And you can see this is quite a bit different because the zones or the regions of my graph are now pie-shaped instead of rectangular shaped. But all these other rules still apply. Hopefully you understand about how to do the oblique asymptote behavior. Okay. I said I was going to mention an alternate way of doing this, and this is the way I used to do it as a student. What I would do, I would just pick out a point, or 2 points. One far off to the right, and I'd say, okay, how about x equals 10? Okay, so that I can see if, that's going to be telling me what's going on with this. The graph, is it approaching from above or below? So I do 2 calculations. One for the oblique asymptote equation. So I'd plug in x equals 10 here. So y would be 14. So that would be the y value at the for the actual line, the oblique asymptote, and then I'd plug in x equals 10 in the original equation for where my curve is. I would get 13 times 8 over 7. I'm not going to do that calculation, but it will turn out to be higher than 14. So I know that if the line is at 14 and if the oblique asymptote is at 14, but I just calculated my graph is at, say, 14.2, well, I know it's approaching from above. And I do the same thing for down here. Plug in a value, x equals -10. Put that into my oblique asymptote, so y equals, I don't know, -6. And then plug in -10 here and see what I get. And in this case, it would actually be lower than -10, sorry, lower than -6. So I know it's coming from above. So if that makes more sense to you, go ahead and do it, but you do have to show your work. Okay, I don't want people just guessing at what these are or looking at the graph and saying, well, it should be this. Okay, I need to see some evidence as to why it is that way. Okay, last example. And this is obviously another oblique asymptote. Okay, so this time our equation is 3x squared plus 4 over x minus 2. I cannot factor anything here. 3x squared plus 4 cannot factor, and it also can't equal 0 because 3x squared will always be 0 or positive, and this is always 4, so the lowest this could ever be would be 4. Okay, so I can actually get zeros here. Now, so if I'm doing my regular work, vertical asymptote at x equals 2, because that factor value of x equals 2 will create a undefined value for that function. Now I can see from the degree here, and I'm not going to go through the same case, 3x squared over x, I can see the degree is 1 higher, so I know I have an oblique asymptote. I'm actually going to do the work down here, so the division, long division. So I have 3x squared plus 4, but remember I have to put a placeholder in because there's no x term here. Okay, so I put plus 0x, if you remember back from that. So 3x squared plus 0x plus 4 divided by x minus 2. So I'm going to multiply by 3x to get my 3x squared. Then 3x times -2 is -6x. Subtract, we get positive 6x, bring down the 4. Now I'm going to multiply by 6. 6x minus 12, remainder of 16. Okay, so there's my rough work to get the oblique asymptote. Bring that up here. So now I know the oblique asymptote is 3x, y equals 3x plus 6 with a remainder of 16 over x minus 2. Okay, x-intercepts. Okay, so the x-intercepts happen when the numerator can be 0, and we just talked about that. It can never be 0 on the top, so therefore there are none. There are no x-intercepts. Y-intercept, if we plug in x equals 0, we get 4 over -2, which is -2. Vertical asymptote behavior. So as x approaches 2 from the negative side, y approaches some infinity. As x approaches 2 from the positive side, y approaches some infinity. If I plug in 2 from the negative side, it would be like 1.99. The top is always going to be positive. We've talked about that, so I don't really need to plug in anything. But the bottom would be negative. Okay, so positive or negative is negative, so this approaches negative infinity. Okay, and then as x approaches 2 from the positive side, so use our sample value 2.01. This time the denominator is positive, top's positive, so we're approaching positive infinity. Okay, and then the end behavior. So this is our oblique asymptote, what's going on. So as x approaches negative infinity, y will approach the oblique asymptote from some direction as x, sorry, I forgot the x. Okay, so now we're going to test it out for the second time. Okay, so if I simulate this situation as x approaching negative infinity, I'll use negative 100. So if I plug in negative 100 for the remainder, I'm going to get 16 over negative 102. Okay, and that's definitely negative. So I put a negative sign. It's coming from below the oblique asymptote. If I simulate approaching positive infinity, let's plug in positive 100. We get 16 over 98, which is definitely positive. So you can see how quick that is compared to trying to do plugging in your number twice into two equations and comparing. So this is faster. Okay, so I'm going to do the sketch now. And this is a strange looking graph, so I'm actually going to make it pretty big. Okay, and I think I'm going to go up by 2's again. So 2. Okay, x, same scale, so 2. Okay, so again, first thing I'm going to do is draw the asymptotes. So we have a vertical asymptote at x equals 2. Okay, not the best job, but it'll do. Okay, so that's my vertical asymptote. And then the horizontal, sorry, there's no horizontal. Oblique asymptote, 3x plus 6. So I have a 2, 4, 6, a y-intercept at 6. That's actually not a point. And then plus 6 means, so if I go over 2, this is going up 12. Okay, so this would be 2, 4, 6, 8, 10, 12. So it's up here. So it's very steep. So it's going up 6, and it's going down 6. 1, 2, 3, 4, 5, 6 for here. Okay. Might have been on the completed version in the that I've given you, I've used a different scale. Okay, so I can extend this out a bit. You can see it's a pretty strange looking graph. I think the version I did on the completed version is a little bit better. So let's start putting in our points. We have a y-intercept at -2. That's all we have for points. We have, as x approaches the vertical asymptote from the left, we're going down, so I have an arrow here. As I approach the vertical asymptote from the right side, I'm heading up to positive infinity, so it's up here. And then the end behavior, as I'm going towards negative infinity, y is approaching the oblique asymptote, which is here, from below. So below is right here. And as I'm heading off to positive infinity, I'm coming from above. Okay, so just barely fit that on the screen. You can see I've got 2 arrows in this pie-shaped region. I have 2 arrows in this pie-shaped region plus a point. This isn't really a point here, that's just from my oblique asymptote. So I'm just going to do my best job to connect these. And then it's pretty hard to do symmetry across this, but something like this. Okay, so that's what the graph would look like. Again, totally strange looking shape compared to what we've done in previous examples, previous lessons. So hopefully that makes sense. I've attached a worksheet that you can practice sketching different rational functions that have all sorts of asymptotes, and some have holes. So this is just to get some good practice of the stuff we did this lesson. Okay, so that'll be it for today. The next lesson we do will be looking at solving rational equations. Have a great day.